This is a video on verifying a series is a solution to a differential equation. The question states, show that the power series y is equal to the summation from n equals 0 to infinity of -1 to the n, 4 to the n, x to the 2n over 2n factorial is a solution to the differential equation y double prime plus 4y is equal to 0. So whenever you want to show that something is a solution to a differential equation, we have to plug in. It's easy to plug in y, but we need to plug in y double prime, so we need to first find y double prime. So let's go ahead and do that. The first thing we do to find y double prime is find y prime. Notice that there's a summation. There's -1 to the n, 4 to the n, and 2n quantity factorial. Those are all constants because the variable is x. So we're only taking the derivative of x to the 2n and then keeping the constants. And the derivative of x to the 2n is 2n x to the 2n minus 1. So what we can say is that the derivative of y is equal to the summation n equals 1 to the infinity. 1 because when we take a derivative, notice that we started with an x to the 2n, and if n is 0, that part goes away. So that's why we start at n equals 1. So n equals 1 to infinity of -1 to the n, 4 to the n, 2n, x to the 2n minus 1, because the derivative of x to the 2n is 2n times x to the 2n minus 1, over 2n factorial. Notice that these constants stayed. I need to find y double prime, so then I take a derivative of the derivative. So y double prime, so now if n is 1, we get x to the 2 times 1 minus 1, which is x, and that does have a non-zero derivative. So we actually are starting at 1 now. So n equals 1, we do not boost it up to 2, to infinity of -1 to the n, 4 to the n, times 2n over 2n factorial. That's these constants over here. And then we take the derivative of x to the 2n minus 1, which is x to the 2n minus 2, times 2n minus 1. So we need to deal with this, and we need to find out how to add these two guys. But y starts at 0, and y double prime starts at 1, so we need to adjust. And the way we adjust is we substitute n minus 1 for n, so that if n starts at 1, n minus 1 starts at 0. So then we really can say n equals 1 to infinity. And I have this 4 because we want 4y, so there's my 4y equals 4 times the summation n equals 1 to the infinity. And then, everywhere we see an n, I put an n minus 1. -1 to the n minus 1 now. 4 to the n minus 1. X to the 2 times n minus 1 over 2 times n minus 1, all factorial. So now we just got to do a little bit of basic algebra. So what we can do is one is take the 4 times 4 to the n minus 1, and that's 4 to the 1 times 4 to the n minus 1. 1 plus n minus 1 is n. So that's a 4 to the n. We can take the -1 to the n minus 1 and say that's -1 to the n times -1 to the n minus 1. Well, -1 to the n minus 1 is just -1. So I can write that as negative times -1 to the n. And then 2 times n minus 1 is 2n minus 2. And 2 times n minus 1 again in the denominator is 2n minus 2. So we're pretty close to being there. But we want to be able to say this 2n minus 2 factorial, we need it to have the same denominator as y double prime, which is 2n factorial. So 2n factorial starts at 2n, and then times 2n minus 1, and then all the rest are the same as 2n minus 2 factorial. So what I do is I multiply top and bottom by 2n times 2n minus 1, And that makes my 2n minus 2 factorial a 2n factorial. So now I can write down that 4y is equal to the summation from n equals 1 to infinity of negative 1 to the n, 4 to the n, times 2n times 2n minus 1, that was the adjustment for the 2n minus 2 factorial, x to the 2n minus 2 over 2n factorial. So I'm pretty much there at this point, because now I can just look at it and see that if I take y double prime, which is this big boy, and I add 4y, well, those are exactly the same except this negative sign right here. So if I add something plus the negative of it, I get 0. So I can conclude that when I plug in this power series, y equals the summation n equals 0 to infinity of negative 1 to the n, 4 to the n, x to the 2n over 2n factorial, into y double prime plus 4y, I get 0. And therefore, that power series is a solution to the differential equation. And I'm done with the problem.